Thank you. Who do I know and trust? Daniel, can you hold this for me? I'm lost without a timer, so thank you. So I've already been introduced, so I will skip that part. Hello, everybody. I'm going to talk to you today about Mythril. It is a static analysis tool that we're developing. Yeah, I like that, right? Okay, thank you. Higher, higher. Yeah? It's like right on my face, right? We talked about this. Okay. I can tell when I'm audible enough. Sorry. Mythril. What am I doing? Like, thank you for your patience. Thank you. Okay, so Mythril, it's a tool to help you find bugs and verify security properties in your contracts, which I would highly encourage you to do before somebody else does. Before somebody else does to your contracts, because they're on the public chain. So this talk is based on a presentation and a paper written by my colleague Bernard Mueller, which was presented at Hack in the Box and then thoroughly torn apart and repackaged for this very different audience. And if the rest of the talk sucks, at least my ASCII art is awesome. So what I'm going to talk about, I'm going to talk about very briefly symbolic execution as a static analysis technique. We talked about that a lot yesterday, so I will not go into that in too much detail. And then I'm just going to burn the rest of my time showing examples of how you can make use of it. So first of all, symbolic execution, what is it in brief? What is it in brief? If you think about a simple program like this where we have an input I, essentially we're going to take this simple logical control flow program and we're going to think about it as a tree of possible states. So we have this I as input, we derive X from that value I, and then we can look at the various ways that we will trace the logic here as we move through the program. So in a bit more sort of a rigorous definition, per Wikipedia, symbolic execution is a means of analyzing a program to determine what inputs cause each part of a program to execute. It is done by assuming symbolic values for inputs rather than obtaining actual inputs, and thus we arrive at expressions in terms of those symbols for expressions and variables in the program, and constraints in terms of those symbols for the possible outcomes of each conditional branch. In the EVM, it looks like this. We put things on the stack. I'm going to move a bit quicker to get to the good stuff. So it's symbolic because, what the hell? It's symbolic because we're not using the value 1, we're looking at it as an argument and tracking it through the program and saying, well, it could be this and it could be this, and based on that, this is something that might happen. So this is actual output from the Mythril tool. It's going to break down our program into these branches. It has these paths that we can traverse, and it gives us these logical statements that describe the conditions for which must be satisfied in order to reach these sections of the code. And so here, if you kind of look at this closely, you'll probably recognize it as Solidity's sort of standard function dispatching thing. I have this function ID, it's the first 4 bytes of my call data, and so that's how I'm gonna travel through to here, and that's where I'm actually running the function add to. So how can you actually use it in your day-to-day, or at least at the end of your development process? One, you can visualize your control flow, so just like we just saw, I'm going to generate a graph of my Solidity file. It looks like this, and I can play with it. So I can get a feel for it. It bounces around. I feel like I know it better now. We can do assertion checking. If we look at this code, how many people know well the difference between solidities require and assert? Is that, like, okay, good number. The difference as I see it is like require you can use fairly liberally. It's meant to like guard against sort of inputs that you don't want. But asserts are stronger statements about invariance. These are things that never should be false. So you should always, you're saying like, I never want this statement to evaluate to false. Should I just stop adjusting it, or like when it gets quiet, what's best for you? Just carry on and like let it fall slowly? Okay, thank you. So we'll look more closely at assertion 2. It's literally just falling on my face. At assertion 2, and we can prove that certain assumptions always hold about our code. So let's see, can this statement ever be false? What do you think? So we have this requirement that our input value is greater than 256. So is it always true that our input times 4 will be less than or equal to 1024? It's essentially, is there an off by 1 error here? So let's check it out. So the path formula for it looks like this, which resolves to this logical statement, which really means that the input must be less than 256 and also not less than 256. Is that possible? Anybody? No. All right, so this is how we can do that analysis with these commands. And so what we see is that an exception is triggered for this location in the code, which is line 4. So it's there, but actually down here we never have that situation. So we feel good about ourselves. So more complex path formulas. This is an awesome challenge. If essentially, like the challenge is for you to find a string as input that will call a suicide opcode. So we're doing this, and we're going to visualize the code. I did want to actually show that. So it's linear. Interesting, it's linear. But when we look at it, we see that there's tons of path conditions. What's going on there? What's with this column of path conditions? So let's actually break it apart. We'll specifically look for a suicide opcode that we can reach. We're increasing the depth. The depth is how many jumps or calls we'll look at. The state size can really explode if you go really deep, but we'll make an exception in this case and look for it. And it's cranking away deeper and deeper into this bytecode. And there it is. Yeah, so it found the suicide instruction, and it gives us down here the value, the string. The string is THC. Wow, such EBM skill. It just told us that. We didn't even have to really think about it. So to be direct, like that's the input that will get you to the suicide opcode, and it just like runs a loop all the way through these various gates. So formal verification, this is probably the only, the last thing I'll be able to do, and I'm going to have to churn through it pretty quickly, unfortunately. So I'm going to make this code as clear as I can. It's a token. In slot 0, we have an owner address. In slot 1, we have a manager address. And we have this strange dynamic array called bonus codes. What up with that? Also important, we have this withdraw function, which only the owner can call, typical Solidity sort of format, pattern. And then we have these bonus code management functions, which only the manager can call. So let's write a functional spec for that. So only the contract owner is authorized to withdraw Ether, and the owner address cannot be changed from its initial value. So there's a bit more formal writing of it. And so we can now write a script, import some Mythril libraries, pull in our Solidity code, and then what we're going to do is we're going to crawl through all the nodes. Laser will split it up into the various nodes of the program. And it's going to look for inputs that lead to a storage writing operation, which is always, a bit of a risky place in your code. And then it's going to say, okay, can we get there and have the top stacked value be 0, which means that we will be able to write to the 0 storage address where our owner address was. So let's look for that, and here's the output, and yes, we can. We find that these 2 inputs will actually allow us to achieve that. So how did this happen? What we see here is that this is actually always true. This is a tautology. It's a pointless thing to check for. Yes, positive numbers are greater than or equal to 0, or integers are greater than or equal to 0. And so then what happened, we actually underflowed the length. We said, what's 0 minus 1? Turns out it's a tremendous number. And so that means that this array, this bonus codes array, we can actually just write to any location in that array. Which means we wrap around. I don't have time to go through this thing, but we wrap around and we overwrite the owner address, and we own the contract now. Reentry, how many times have you guys seen this in the past week? Reentry, yay. So it is interesting to define it more clearly for the sake of static analysis. We make an external call to a user-supplied address with high call gas. So that's something that we find risky. I've got 5 minutes? Wonderful, thank you, sir. That's something we find risky. And then what really makes it dangerous is a state change after that external call. So there is reentry that can be benign. I don't know if it's necessarily desirable, but there are specific cases of it that we're especially worried about. So we can look for this, we can run it. Mythril, that's X is for an analyze, and it does in fact find it for us. The return value of an external call is not checked. That's dangerous is essentially what it's saying. And notice, like, that was just a command line. Like, it was just right out of the box. It's going to check for reentrance for you. It's just myth-x your contract. It's dead simple, and so it's easy to get started. But then you can do these more sophisticated analyses, as in the formal verification example. Just a couple sort of more sugary, fun features. There's a symbolic trace explorer. It kind of combines the graph view with debugger-like functionality of Remix. And not yet, but what we will eventually be doing is enabling you to click on a branch in the code that you think is interesting and say, how would I get here? So you can actually just zero in right on those places within the code that are really high risk. And it'll solve for that. We've also have plans to develop or create developer tools for you to make this easier. So it's going to be really pretty one day. So that's my presentation. So I would highly encourage you to use Mythril to find bugs and verify security properties in your contracts before someone else does. If you found this interesting, there's more information here. Please check it out. And we'd love, if you're interested in this stuff, please come join us, build this, or help us use it to break other people's contracts. It's really, really fun. Of course, please come talk to me afterwards. Thank you.